Okay, we're going to take a look at a practice problem for masses on springs. And it's the first one on the practice set that I pass out in class. Let me share it with you for a moment. Oops, wrong one. There we are. It is a 1 kilogram object is attached to a horizontal spring. The spring is initially stretched by 0.1 meter. And let's see, it proceeds to move without friction, and it's released from rest at that point. Alright, so that actually tells me that's probably the amplitude, 0.100 meter. And released from rest at t equals 0. It proceeds to move without friction, so it's the type of oscillator we've been talking about. The next time the speed of the object is 0 is half a second later. So next time v equals 0 is at t equals 0.500 seconds. We are trying to find Vmax. Alright, so what is the maximum speed of the object? Yes, the answer is right there, but we're going to figure it out for ourselves. So here are the givens. If we imagine the situation, we have the spring, we have the mass. It's initially moved so that it is stretched out some distance. So we'll say that it's moved from here to there, 0.1 meter. Alright. At this point, v equals 0, t equals 0. We allow it to move. And if we think about it, where's the next place it's going to go through 0? So v equals 0. Those are going to be turning points. So x is kind of a cosine function, so it's oscillating up and down, which means that, its velocity is also going to look something like that, but kind of out of phase. So we're looking for places where we're getting 0. And those are going to correspond to turning points. Places where we are at maximum, like we were here, or minimum. So 0.5 seconds corresponds to when we have moved negative 0.1 meter. Alright, how much of a cycle is that? Well, we're going from essentially our peak and coming down into a trough, and that represents half a cycle. So that means 0.500 seconds is equal to the period over 2. So the period is, oops, one too many zeros, 1 second. Okay. Got to think your way carefully through that one. You have to think about, okay, so those v equals zeros are turning points of like a cosine function or a sine function. They're places where we're at our min or our max. And that means we've gone half a cycle, not a whole cycle. Alright. So we know the period, and that is great. We know the amplitude, and that is great. 0.10, oops, 100 meter. Alright. We also know m, and if we're trying to find Vmax, that is equal to the amplitude square root of k over m, or if you prefer, a times omega. A times omega is actually what we need here. So a could be rewritten in terms of, oops, not a could be rewritten. This could be rewritten as 2 pi times the frequency, using our first video on the chapter, which can be rewritten as 2 pi over the period, because frequency is 1 over period. We know A, we know period, 2 pi is a constant, so we should be able to find our answer here. Alright, 0.1 divided by 1 is trivial. 0.1 times pi is going to be 0.3145. Times 2 is 0.628, basically. So 0.628, and units are meters per second. Okay. So the second example problem is taken from a textbook's example problem, so you may have seen it already, depending on which school you're at and what you're reading. It has a little bit of a wrinkle on the idea. Oh, it's a similar problem to this in many respects, and I'll let you work on it for yourself, but practice problem number 2. The springs are kind of set up vertically. So I want to address the question, how does vertical spring change things? Well, you'll learn when you solve differential equations in your actual differential equations class that if you know the homogeneous solution and then you have one that isn't equal to 0 anymore, if that's a constant, it's actually not too bad. And instead of having x is equal to a cosine of omega t plus phase, just like that, you'll also have plus some offset that will depend on the additional force. And in this case, we basically have the equation looking something like second derivative of x with respect to t plus k over mx is equal to, g. And it gives us an offset that's related to that g factor. Essentially, it's how much you're already stretched or compressed by gravity. But here's the important thing. Has not changed omega, the rate of oscillation. So, like in example problem 2 or any other future problem with a vertically hung spring, you don't need to worry about omega being changed or the period being changed or the frequency being changed. It affects sort of the initial position and the offset you start at, but the fact that you have it hanging vertically does not change any of the properties of the oscillation itself. Essentially, instead of having something that's oscillating about 0, you now have something that's oscillating around an offset point. That's all it does, nothing special. Alright, so that's about 8 minutes in, and I think I'm going to stop the problem there. We've got our answer. We could play around and find the maximum acceleration if we wanted. We could actually take the information we've been given at this point and find the mass. So let me suggest that as an extra problem for you to try. Sorry, not the mass, the k, the spring constant. Given what we figured out, could you find the spring constant knowing that the period is 1 second? Could you figure out the spring constant? Mass 1 kilogram, period 1 second. What would k be? Alright, that's it for this one. See you in the next video.